Okay, welcome to the Oxford seminar. This week we're hearing from Matteo, who will be telling us about two classifiers for two algebras.
All right, thank you. It's very nice to be speaking here. It's very nice to be here too, but I can say it's a second home now, since we established that. No spoilers, no spoilers. So why the abstract study of compositionality and as a subtitle of my talk, aka let me give an introduction for what I'm about to tell you, which involves a lot of abstract two-category theory. So as you might suspect, I'm involved with David and other people in the study of double categorical systems theory, also known as dots nowadays, right? Which involves basically algebraic structures. There are these theories of systems and maps between them. And these maps eminently usually land in something that's like set, because these maps are used to talk about behavior of systems, okay? So there's this idea of functorial behavior being a way to represent your notion of like semantics for your systems, or like to give like a dynamical meaning to the algebraic representation that otherwise a theory of systems is. And also, since it's a map of algebras, it has all these interesting features that map of algebras, I should say two algebras have, which is that you can talk very explicitly about preserving or not the algebraic structure, right? Or rather preserving it on the nose, preserving it up to ISO, preserving it up to a comparison. And this directly translates into being able to talk about not just what behavior is, but also how it relates to the compositional nature of systems, right? Which is the study of compositionality. So what is the link between what I'm about to say and all this theory is the idea that first, first we want to show that theories of systems have a two classifier in them, which means that you can talk about behavior as if it was like a generalized version of a Capucci, okay? Second thing is you can now study you can now study compositionality of behavior from a purely abstract point of view and characterize specifically when is it that behavior is compositional, when you construct it in a certain way, which is when you construct it as a representable. Okay, so as we all know, Capucci's like the special kind of Capucci's are the representables, which are special for two reasons. First, because you can build any other Capucci out of representables. Also because they're really easy to construct, right? They're just there. And the same applies here. And like representable behavior has been like one of the main driving themes of the double theory of systems. And so if we manage to understand better how when is a representable behavior compositional, then we're doing a lot of interesting work towards understanding compositionality of behavior. Okay. So maybe you should also mention, I gave a talk about representability at Topos like 4 months ago. This is sort of a follow-up talk in a sense, because like there I gave a bunch of, like I worked out by hand a bunch of like conditions that give you compositionality. And this is a more like uniform and organized approach to working out those compositionality conditions, right? And the final result will be that indeed those compositionality conditions are sort of sufficient and necessary at the same time, which is good. Final thing, this is all kind of work in progress, so this is like 80% done, but there's going to be like wrinkles, and like the final application to systems theory is still like to be written down and everything. Everything else you can find on the forest. So you can follow along with your forest now, if you have access to the Topos forest. Okay, so let's go. No. Okay, two classifiers in enhanced two categories. In England, everybody knows James Bond. And James Bond always wears this kind of watch, which is an Omega watch. And Omegas are really important in this talk. So here's why I put this. But let's start from the beginning. So this talk will take place in the wonderful world of enhanced two categories, also known as F category, which I think here we all know and love. So an enhanced two category is just like, it's something very simple. You have a two category and you want to distinguish some one cells. They're particularly nice, so you call them tight. And then it was shown by Lack and Shulman that there's a whole yoga around this notion that you can perform based on the fact that this choice corresponds to an enrichment in a certain category, which is this category, this category F, which is literally the category of faithful and identity on objects, right? No, injective on objects, locally faithful functors. Okay, so this is what an enhanced two category is. And we have a notion of functor, which is a two functor that preserves tightness. We have a notion of natural transformation, which is a natural transformation, but it's a two natural transformation with tight components. We have a notion of monad, which is like the enriched notion of monad. And what is it then? It's a two monad whose carrier preserve tightness and whose structural morphisms are tight as natural transformations. And the reason we're interested in this is that from every enhanced two monad, you can build an enhanced two category of algebras. And this is very, very useful because this is, like, I think the most elementary setting in which it is really useful to distinguish between tight and loose morphism. So let's see what this alt-LT is. So this is just your common two category of strict algebras and lax morphisms for a two monad. But we are marking as tight those maps that are strict. So among the lax morphisms, we are distinguishing the strict ones. And we do not think on the objects, we do not think on the two morphisms, okay? So second of all, discrete opfibration. So this will be, I would call them DOS or TDOS from now on. If you see me saying that, you know, this is what I mean by TDOS is a tight discrete opfibration. So if you're in enhanced two category, you can talk about discrete opfibrations, just like in CAT. Okay, so in CAT, a discrete opfibration is just a functor whose fibers are discrete, but you can give the same definition in any two category by saying that you have a one cell such that every two cell like this has a unique lift of this kind. Okay, so you can sort of push forward E along phi and get something over B. Now, in an enhanced two category, you have a tighter notion where you say, well, I want my discrete opfibration also be tight. Okay, so this is what a tight discrete opfibration is. And then a special case, very important special case, is the case of representables. So first of all, let me say that I freely employ the name object for any one cell in a two category, right? So just like elements of an object in a category are just maps into it. In a two category, objects of an element of objects of an object of the two category are one cells into it. So if you have a one cell into B, aka an object of B, and you take the comma over the identity of B, you can build this one cell here, which is always a discrete opfibration. And I call it, well, everybody calls it, I think, representable discrete opfibration. And specifically when B's identity, one gets the domain of fibration associated to B. When B's identity, we get B over B, like big B over big B, which is also the arrow object associated to B. So this is a very important class of discrete opfibrations. Let me also mention that. So later on in the talk, I'll make more precise which enhanced two categories I need to perform the constructions we'll perform. But specifically, so here to form this representable fibrations, we need commas, and notice that this discrete opfibration will be tight as long as B is tight, and this is a tight comma. Okay. In the forest, you find a slightly more refined notion of this, of like a comma in which you have the left leg being tight, but this could be loose, and you get a tight projection and a loose projection out of it. So that's all you need in practice for what I'm about to say. But it's just to say, the representable opfibration is at a tight object is a tight discrete opfibration. Okay, so this is the slogan. Now, what is a two classifier then? So the idea is that we should think of discrete opfibrations pretty much as generalizations of subobjects, right? Because a subobject is a family of propositions, right? Indexed by, or rather, it's an arrow whose fibers are propositions. So things that are like one-dimensionless in the ambient, like the other objects, but here we have everything up one dimension. So because we're working with categories. So now we look at fibers that they're not propositions, but are sets. Okay, so I have homotopy dimension 0. Now, well, the notion of subobject classifier is very old by now, at least 80 years old, I guess. But the notion of discrete opfibration classifier is much more recent. I think it's due to Weber, but maybe it's not. Who knows? But certainly Weber in his 2007 paper about like Yoneda structure and two topoi gives this definition, which is explicitly a generalization, like a categorification of the notion of subobject classifier. But here I'm gonna use mostly the equivalent characterization those Weber like gives, but that Mezziti really puts into focus in his paper from last year, which is that of he calls it good two classifier. I call it just two classifier. And since we are in the enhanced two categories, an enhanced two classifier. What is this? This is just an object omega plus a tight map into omega from one, the terminal object. And the idea is that you want an equivalence between one cells from B to omega and tight discrete of theta over B. Okay. And the way this is given is by taking commas, right? So given a theta here, you can find a unique, an essentially unique name for it, which I call dp because it's like the differential. Why is it the differential? Because when we go the other way, this generalizes the growth and deconstruction, which is like an integral, right? So that's it. So given P, we find an essentially unique functor, cell from B to omega, such that taking the comma recovers P, or rather such that this is a comma, right? And vice versa for every such one cell, we perform the comma construction and we get tight discrete opfibration, but that's like given. Now, when P is representable later on, I will call like the name of P y to the B, right? Because it's sort of the representable Cooper sheaf, right? So yeah, by the way, let's make this analogy a bit more clear. So the archetypal example of two classifier is that of cat with set and the inclusion of the one singleton, right? So and this recovers the fact that discrete opfibrations over a category are equivalent to Cooper sheaves out of that category. And you go back and forth by either taking fibers or by performing the growth and deconstruction, which gives you the category of elements of F. All right. Now, here there's no tightness around because cat is a so-called chordate. Well, we take it to be a chordate enhanced two category, but you get the idea, right? So the only difference from a two classifier enhanced two classifier is that we limit like the things we want to classify. So here is also another example which is a bit less trivial. So in Mazzitti's paper, he shows that any category of Copri stacks, which is such a bad name, but we can call them index categories, there is a 2 classifier, which is basically inherited by cat, right, from cat. And so this is an index category that over C takes its value over C is Copri sheaves out of the slice under C. Okay, C little c the object. And then you can reindex by precomposing by precomposition with a given morphism. Okay. Yeah, and the actual properly speaking classifier takes picks for in every omega c, which is this object of Copri sheaves, it picks the terminal one. Okay. Now this construction is very useful because often 2 categories of interest can be written in this way. And this is, for example, the case of graph cat. So graphs of categories are indeed categories indexed by the walking graph, which is this thing. Now imagine there is an S here and a T here, naming the 2 arrows, which I was too lazy to do. So if we perform this construction above, we get that omega E is it's Copri sheaves over this walking span. So it's literally the category of spans of sets. Okay. And omega V is instead just set because the slice under V in this category is trivial. And then the 2 indexing are just picking S and picking T as the set to send down here. Okay. So overall, we get the classifier, the 2 classifier in graph cat for discrete opfibrations, which by the way are just fiber-wise, point-wise discrete opfibrations. That's what it is. It's the large graph of spans of sets. All right. And then we have 1 to omega picking the trivial span. Okay. Is this clear? That's clear. Now, let me also mention this, that the first thing you should do when you have a 2 classifier is classify, well, see what happens when you classify the identity, right? That's very canonical thing to try to do. What do you get is called the generic discrete opfibration, which you could think of as the fibration, well, the opfibration of pointed objects in omega, okay? Where you're pointing by tau. In CAD, this is literally pointed sets projecting out their point. Well, they're set. So you're leaving out the point by projecting out the set. Anyway, the point of this is that you can now use this generic discrete opfibration as a classifier instead. This is what Weber does. Now the classification happens by pullback, right? So if you take a map into omega and you pull back the generic discrete opfibration, you're going to get another discrete opfibration. And in fact, you get all discrete opfibrations in this way, right? And also observe that the classifying morphism in this sense is the same as the classifying morphism in the previous sense, okay? Now, we're going to use this pretty much interchangeably, but I found the comma version to be a little easier to work with. But that's just to mention discrete opfibrations. Sorry, the generic discrete opfibrations. Now, let's move on to the second part, which is about Cartesianity. So we came a long way from René Descartes. And today I want to give you a different perspective, well, another perspective on Cartesianity that I never realized before. So we start from this definition. So now we fix a 2 category, we fix a 2 monad on it, T. And now suppose we have 2 algebras, A and B, and we have a morphism, a strict T morphism between A and B. Then what you can do is look at the comparison map. So a strict T morphism, the fact that F is a strict T morphism means that the outer square is a square. But now you can look at the comparison map with the pullback you get from these 2 things. And we're gonna call this the Cartesianity defect. And of course, when it is invertible, meaning that the square we started with was actually a pullback to begin with, we say that f is T Cartesian. Okay, so this is a notion that I found in the literature in just one place, which is a post on the NCafe by Tom Lenster. Actually, then he put like most of the same material at the end of his paper, one of his papers about Möbius inversion. But anyway, so, oh no. So yeah, it seems it's kind of new, especially it is new in the two categorical setting. Maybe, yeah, I'm giving some examples later, but for now, let's keep this here. The other thing I want to mention to start is that by the result of lack, in algebras with Collatz morphisms, we can always form comma objects of this shape. So it's Collatz arrows over strict arrows. And dually, in algebras with lax morphisms, you can form commas of strict morphisms over lax morphisms. And this basically means that, well, this, of course, if K has those kind of commas, right? So this basically means that you can use the structure of F and S to build an algebra structure on the comma, okay? And you can do so when, like in generality, when S is Collatz and F is when S is lax and F is Collatz. But since we have to choose if we'll Collatz or lax, then you're forced to fix one of to be strict and the other to be the ambient category kind of morphism that you chose. All right. So now we can formulate this definition. So fix an algebra A and consider an object of the algebra, right? And so we are again in algebras with Collatz morphism. So an object of the algebra A is in fact a Collatz T morphism into A. Now we say that the algebra is Cartesian at the object A when the representable discrete opfibration at A is a T Cartesian morphism, which boils down to that diagram being a pullback, okay? Now, what does this mean? I'm going to give you an example. So consider FAM, the free coproduct completion to monadom cat. Now, a category with coproducts is a FAM algebra, and I claim that it's Cartesian at the identity seen as a generalized object when it is strictly extensive, where strictly extensive means that instead of there being an equivalence between the slice over a coproduct and the product of the slices, there is an actual isomorphism of category. So this is a bit of a quirk of the definitions that I chose, because if you choose a different kind of pullback, you actually get the equivalence here. And so you get extensivity. But anyway, so here's the point is to kind of build an intuition for what this Cartesianity condition is. So let's see what this amounts to. So you take this A with like its FAM algebra structure, which is just taking coproducts of families. And now you're looking at the pullback of this along its codomain opfibration. And now the comparison map delta of del 1 is the Cartesianity defect, remember? And what's that doing is the following. So you take a family of arrows. So you take an indexing set and a family of arrows in A. And the Cartesianity is sending this to the family of its codomains and the coproduct of the morphisms, okay, which is an arrow in A. Now, if you want this to be invertible, we're saying that for every arrow from a given X into a coproduct, right, which is what an object here is, there corresponds a unique family of arrows from a family of X's into the family of y's that we have a coproduct of here, such that psi is in fact the coproduct of these, right? So the usual definition of extensivity is you have an isomorphism here, right? Specifically, like you have an isomorphism between these x and the family of xi and the coproduct of the family of xi's. So again, because here we're talking about strict extensivity, or rather, because we chose this kind of pullbacks, now here we have inequality. So we see that what we recover is strict extensivity, okay? So the general idea here then is the fact, like Cartesianity, in the sense that I defined above, has something to do with the way that terms of arrows, in the sense of T, the monad, and arrows between terms, but especially into terms, relate, okay? So here's another example. So suppose we're looking at global objects now. So X, which is the domain of the object A, is 1, right? So, well, in general, this is what I told you, right? So this is what Cartesianity sort of entails, that if you map from A into a term made of other things, this is the same as the term made of maps into each of the free variables here, right, from A. This is kind of like informal as a notation, but also it isn't. But think of this as, so like the classic case, and this is why it's called Cartesianity, is T being the free symmetric monoidal category 2 monad, okay, which is a long way to say, suppose that these are maps in a category and T is actually like take the product, like a monoidal product. What do we call a category in which this is the case? So if you map into a product, then it's the same as the product of the mappings, like the home sets, into each of the factors of the product. We call that a Cartesian monoidal category, right? So a Cartesian algebra for the free symmetric monoidal category to monad is in fact a Cartesian monoidal category, right? And also notice this, that what we're basically saying here is that the representable at A is a strong T-morphism, right? So here you start to see why this notion is relevant for the thing, like the motivation it started from, right? Like at the end of the day, Cartesianity is sort of a compositionality property for co-representables. And this is actually the last result I will present today. So as another example of this notion of Cartesianity, let's look at double categories. This is nothing of Spanish or span-like double category, which is a double category that has this property. So if you map out of an identity, a loose identity, so a unit, into a composite, then there is a unique way to split this square into a composite of two squares, each of like coarity 1, okay? So the short version is mapping into a composite is the same as mapping into each of the composites. And this is very relevant in, so this is from David's book also, and this is very relevant in categorical systems theory, because at the end of the day, you realize that a lot of the compositionality property for parameter settings, you call them like this.
Coupling laws, wiring diagrams.
Wiring diagrams for those kind of systems then like hinge on this property. But anyway.
Yeah, parameter setting systems.
Right. But anyway, so can we recover this from Cartesianity? Yes. So you take the free double category to monad on graph cat, and now we consider a strict object of a double category A. What is a strict object is just a map from the terminal double category to A, and therefore it just simply picks an object of A. And now to say that this is FC Cartesian, so again, I was lazy and I didn't draw all the nice diagrams for the FAM example, but imagine what this is. We're saying that the free category on the slides, which is, suppose you have a bunch of mappings like this one, okay? And you compose them. So you have a string of these squares like this. And I want to say that this is exactly equivalent to mapping like A over FCA. So this is exactly equivalent to one map into the composite, okay? So again, this is an instance of this concept here, mapping into term, the same thing as a term of mappings. And therefore, this is an instance of the Cartesianity concept, specifically a double category Spanish, if and only if it is Cartesian at every straight object. Okay. Now, the fact that we have to pick straight objects is a bit of a wrinkle here. So here's a couple of results to understand better just that thing. So maybe I should say it like this, that what you like to really do, for example, in a Cartesian monoidal category, you don't say, well, pick a comonoid in the monoidal category. Now, if it has this property, then the monoidal category is Cartesian. You say pick an object, right? An object is in the object, an object of the category, not an object of the monoidal category, right? So I want to show that, in fact, you can define Cartesianity for objects of the carrier of the algebra rather than objects of the algebra, okay? So you can reformulate the Cartesianity condition in this way by saying that, by observing that being Cartesian in A for an algebra big A is equivalent to requiring that this square is a comma. And this is just an observation, like you paste the square here. The only thing you should observe here is that this does not involve the collaxator of A, right? Nowhere we need that. So you can give a definition of Cartesianity that doesn't involve, like just for what I call unstructured objects or objects of the carrier. So this is where we're going to get at a generalized reverse Fox here. I'm going to tell you what that is. So we need properties on T. So we want T, the monad, to be Cartesian at the representable discrete opfibrations, which means that the naturality squares for I and M unit and multiplication of T have to be pullbacks at representable discrete opfibration. Okay, so every morphism of K gets its own naturality square in I and its own naturality square in M, and you want those to be pullbacks, okay? So when that is the case, then you can in fact show that if you have two T algebras and you have just a map between the carriers, so an object of A of shape X, then if this square here is a comma, then in fact, A is a collax T morphism in a unique way, and A, the algebra, is Cartesian at A, okay? So why am I calling this a generalized reverse Fox theorem? So Fox's theorem is the theorem that says that a monoidal category is Cartesian if and only if, well, yeah, when every object is a commutative comonoid in a unique way and every map preserves the structure. So the reverse Fox theorem is the very classical observation that in a monoidal category, that is the case, right? That every object is in fact uniquely a commutative comonoid, right? Mm-hmm. So this is what we're saying here. We're saying, well, if your T algebra is Cartesian at an object, right? Then that object is in fact T structured, well, T co-structured, right? So the T co-structured object for T, the free symmetric monoidal category monad, is a commutative comonoid, right? So this is this, but in the generality of like two monads, Cartesian and representable discrete opfibrations. And now the only thing I want to show you from the proof is how you construct the unique collaxator, because we're going to use this later. And the way you do it is as follows: like you consider the identity square of the arrow A, which is this outer square. There's going to be a comparison map picking out like this identity in the coslice over A. Now you take T of that, right? And you get this map here from Tx to T of A slice A. And now you whisker the comma that you assumed was a comma. So you whiskered this square. And now if you look at the outer square, this is exactly the square that gives you, like, that you have to fill in order to give a collapse structure to A, right? And the rest of the proof is just showing that this is indeed a valid collapse structure. All right, so yeah, this is, I actually told you this already. And now the point is that it is the same thing now to ask that, like for this class of two monads, is it the same thing to ask whether an algebra is Cartesian at an object, like a structured object, or an unstructured object? Okay, these are exactly equivalent. Okay, let's go to the meat. Any questions anyway? We go with time. Yeah. How long do I have? Sorry.
Maybe 20.
Yeah. Wasn't realizing my battery is running out. Yeah.
You use USB.
Yeah. Well, and this go here. We're back. So David had a question for me.
I did. If we could go to the,
Sure.
well, so you said this is a form of the reverse Fox theorem.
A claim. Yeah.
Yeah. The Fox's theorem says that if you have a natural comonoid structure on every object of a symmetric monodal category, then it is in fact Cartesian. Is that right?
Yeah.
Do you have a sense of whether you could get that out of this?
Yeah, that's an excellent question. I don't. Like, there is a role of commutativity there, which I don't completely understand. Like, in a sense, it should be irrelevant because it's like part of the structure, right? It's like a thing. But it seems to be related to that. Because, like, if you just ask for like a natural supply of comonoids, full stop, it doesn't work. So it's like, maybe it's not about commutativity, but it's about like a property that the T, like the two monad gets when it is about commutative, like symmetric monoidal categories rather than just monoidal categories. See where I'm getting at?
Yeah.
So since I didn't need the converse Fox theorem, aka generalized Fox theorem, I just stopped wondering at some point. But it's definitely a very interesting question that I'd love to understand better. Because like if you apply this result, for example, to double categories, right? You take the idea that Spanish double categories are two Cartesian monodal categories, or double categories are two monodal categories. Well, you see very well that it doesn't work, right? Because if you map like a span, if you have an endospan and you map into like its twice composed thing, well, you can't basically, right? But if you have an endospan whose legs are the same, now you can, which I think is a form of commutativity, but it might just be a red herring. I don't know. But yeah, that's a thing too.
Yeah, you've got symmetry. You can map to like use the symmetric map to one of the vertices and the ordinary map to the other or something. Yeah.
Let's go on. So lifting two classifiers. Right. A plumbus is an enhanced two category, admitting the following two limits: all left-side pullbacks of tight discrete opfiberations, all left-side commas, and a tight terminal object. So we're glossing over left-side for a bit for two reasons. One, because it's a bit boring to define what this pullback is. This is like, and then commas are like a specific way to limit. But also because like it's not completely clear to me why you would need that. Like it seems that you have that and you kind of use that, but this is like one of the parts where the work in progress is in progress. So this is like my best. Yeah, I like 99% sure that this is true, but okay. Just wanted to say this is not like extremely relevant. If you have a better name for plumbus, I'm open to suggest it. This is me being frustrated at terminology. Anyway, so from now on, well, maybe in a second, we're going to work in a plumbus. Oh, important result about plumbus is that if you have a plumbus and you have an enhanced two monad on the plumbus, you get another plumbus of algebras and lax morphisms. And that's just a fact. I think the most interesting part of this is that we get a surprise application of a theorem that me and David proved for another paper, which is that so what we proved this theorem 5.10 is that if you have like strict normal fibrations in algebras with collax morphisms, these pull back, okay? So you dualize this and you get that you have the pullbacks of strict discrete opfibrations along any lax morphisms, right? And then it's like you get this left tightness because they are discrete opfibrations, which is why I think it's a good notion of limit. But again, I'm going to gloss over that. Anyway, this is important because what we want to do eventually is like iterate the theorem I'm about to prove, and then to iterate that, you need to actually being able to like get the same setting you started from in the algebras of the monad that you're lifting your classifiers against. But I'm putting the cart before the horses. So we got a good notion of two-category. Now, what is a good notion of a two-monad that lifts two classifiers? So, well, of course, first, like, assume you have a two-classifier in the plumbus. Now, this opfibrantly Cartesian enhanced two-monad, which is maybe a worse name than plumbus too. What is it? It's supposedly the minimum requirements on an enhanced two-monad in order to have the result we want. Actually, I think that, like, I think I proved this because we'll see a characterization later, which is basically this. But another way to see this is like a sufficiently Cartesian, right? Two-monad. Like we're asking to preserve some pullbacks, so some limits. We're asking it to preserve, like, for its structure morphism to be Cartesian, sort of like the same maps, and we're asking it to preserve tight discrete opfibrations. Okay. So in fact, if your two-monad preserves all two limits, or just like the commas, then this is true, right? Well, and I and M are Cartesian, of course, but like it's 1 and 2 are implied by preserving two limits, okay? But we don't need the whole preservation thing, right? And that's why this is called fibrantly Cartesian, because like enough, Cartesian enough. So here's a characterization. So we're going to prove two characterizations of this kind of two monads. This first is sort of like kind of obvious when you think about it, because when you have a two classifier, every discrete offibration is in fact generated by by taking commas or pulling back from the classifier. Okay, so either by pulling back the generic discrete offibration or by taking commas of tau. Okay, so it's unsurprising in a sense that the conditions here in definition 4.4 can be actually checked at the generic discrete offibration, and that's enough. I won't show you the proof because it's just like use the passing lemma for commas a lot of times. But the most interesting part, which you're gonna need later, is that if you assume 2.2 prime, so that TU, so the image of the generic discrete offibration, is again a discrete offibration. It is tight because T respects tightness. Then you can classify it, and what you get is a candidate algebra structure for omega. Okay. And this is very interesting. Like, I hope we can get to like examples later, but it is really wonderful how this, like, if you actually compute it, it's beautiful. Because what this is saying is basically like omega is taking the fiber over a term, like the points over a term, and that's the image of the term, which is great. There's a universal property hidden here. Not very hidden because we're literally asking it to be a comma, but it's really cool. And in fact, you can show, I think this is the next theorem, that this map omega is a T algebra. Now, is it strict? Maybe. It's like strict enough. If we work with univariate categories, this will be strict. But it's been observed that this might just be a pseudo T algebra, and if you're and you can often strictify it, but you can prove it is lawful as a T algebra, so it's not just an algebra of the endofunctor, by basically showing that, but use the property that it classifies TU and the other properties you ask on T to show equations, the equations you need to prove, which are all equations between classifying morphisms. So you show they are true by showing that those morphisms classify the same thing, right? So if you had a univalent, like if you were working with univalent categories, like we had two categories of univalent objects, then this would be enough, because if two things are isomorphic, then they're actually equal. But in fact, what you get if two things are the classifying morphism of the same thing, from the definition I gave you, this would just prove that they're isomorphic as morphism. So this is more of a pseudo T algebra, in fact. Obligatory disclaimer here. But you see how we prove this. We just use the properties that we assumed. Specifically, we use the fact that I and M are Cartesian at TU. And the pasting lemma for commas. Now I'm saying this because remember that the pasting lemma for commas goes both ways. So in fact, the next result, the other next result, which is here, is that if you ask T to preserve pullbacks at the generic discrete opfibration, you can replace the other two axioms by just asking that omega is a T algebra. Exactly, because then you can prove Cartesianity by running this proof in reverse. Okay, so this is what I say. This is what I mean when I say that, well, in fact, we kind of got the minimal requirements for this, because as we see later, then like this axiom here pretty much directly saying that you have a classifier for Laxmorph, like for in AlgLax. Okay, did I explain myself? Yeah. Sure.
So if we going from the optimally Cartesian to monad, we can get a pseudo T algebra structure omega. Right. But if we started from this one here, we could, when we go back, we could use pseudo, but we could also at this point just pick omega to be some strict one if we had it. And then that's sort of how we can end up with a strict choice or something.
Yeah, I mean, like at the end of the day, these are all the same, because like when you turn this back, that you don't really care that this classify the same thing, you just care that they classify equivalent things, right? And so like we just end up like the moral of the story should weaken everything, sort of, right? But the same applies. But I think the point that you make is, imagine you can strictify, which is not such a bad assumption, right? It's like quite common that you can. Then once you have this, when you have pseudo algebra, then you're pretty much okay, right? Okay, lemma 4.8, which is basically an application of that reverse Fox theorem that I showed you before, is that, okay, in fact, the two classifier is a Colac dimorphism and omega is Cartesian there, okay? So it's an application of the fact that, well, there's like, a priori, we don't know if this is a dimorphism even, right? So that's why we needed the other theorem, basically. But in fact, it is a dimorphism because of the way we constructed omega, which I remind you is this one. So if you squint your eyes, you see that this is saying that omega is Cartesian at tau. But anyway, this is just to say that we have this thing. Proposition 4.9, we already covered that. Finally, let's get to the theorem. So there's one slightly disappointing thing. The other slightly disappointing thing we already mentioned, that is, in fact, you get a pseudo algebra on big omega. You don't get a strict algebra, but you're gonna need a strict algebra. So, well, there's that, and there is the fact that now we have tau, which is colax, as a T-morphism. And now what we want to do is use tau as the 2 classifier in alg-LT, okay? Because maybe I never said this, but like the whole thing is we want to lift 2 classifiers from a 2 category to a 2 category of algebras and Lax morphism. Like that's the goal, right? So this is the point of, well, this is our prize in a sense, okay? The problem is if tau is colax, of course, it cannot be a classifier in algebra with Lax morphisms, right? Because it's just non-morphism there, which hits like a slight wrinkle in like 2 algebra theory, which is that Lax and colax morphisms really want to live in the same structure in some sense, right? And this is a case of that because like commas, as I said before, of is colax under Lax morphisms. Like the construction, like in principle, you can define the comma of that kind of shape, right? Except that it's not a comma in any sense, because of course those 2 morphisms don't even live in the same 2 category. So this is what I say, that they want to form some kind of structure, but there doesn't seem to be a lot of efforts in this direction. An obvious effort is that of Perret and Grandis in this unpublished paper of them about generalized quintets, I think it's called. And yeah, a generalized quintet, for example, is the double category of algebras of a 2-monad Lax morphisms in one direction and colax morphism in another direction. Okay, so that's one candidate structure where these things live. Okay, stretch this too much. The point is, at this point, we have to assume that, like, we have to additionally assume that tau is strict. Okay, so we know it's colax. Now, suppose it is in fact strict. The good news is, for the examples when the applications we care about, that is in fact true. There is also, I don't know, it is plausible that in fact you can prove it is, at least pseudo. But I don't seem to be able to do that. So let's assume that. So just to recapitulate, we have a Plumbus K, we have an opfibrantly Cartesian 2-monad. We constructed this algebra structure on big omega. We notice that tau is a colax T-morphism. Now assume it is strict. And the result is then we get an enhanced 2 category of T algebras. Well, we get a Plumbus of T algebras and Lax morphisms with an enhanced 2 classifier given precisely by tau with this strict T-morphism structure. And the proof is not hard. I'm just gonna give you like the idea. So the first thing to notice is that basically like the classifying map is the same it is in K, right? So the only thing to prove is basically the classifying map is a Lax morphism, which is to say we have to construct a laxator. So here we chose a P tight discrete opfibration, and we classified it in K. And now we have to build this dotted 2-cell, okay? And notice that this dotted 2-cell is a 2-cell between 2 1-cells that end in omega, right? Which is to say they are gonna classify something. And in fact, we know what they classify. So the bottom thing, so dp beta, classifies the pullback of P along beta, okay? And the other one classifies this thing, which is, well, it's at the end of the day, it's just P. Spoiler alert. It's below in the proof, and I didn't screenshot that, but it's just TP. Oh no, actually it is here. Okay, sorry. So at the end of the day, so what I want to say is that this is going to classify something. Okay, it's a two-cell, so it's going to classify specifically a morphism of discrete opfibrations between the discrete opfibrations that its boundaries classify. What are these boundary classifying? They're classifying B star E, which is this pullback, and TP. Okay, and so we need a map like this. And guess what? This map is precisely the Cartesianity defect of P. Okay, basically by definition, right? Because by definition, it is precisely the comparison map with the pullback. Okay. Okay, so this is how you define the laxator, and the rest of the proof is just proving that it is indeed a laxator, and you use just the properties of we required of T and specifically omega. And that's the theorem. Now, what do you read from this theorem? So two easy consequences are this. Well, this is just what I told you just now. Like if you have a tight discrete vibration, which is T Cartesian, then you know its classifying map is strong, in fact. Okay. So this is classifying precisely which like coprochees with algebraic structure are in fact strong. And the other thing is, well, specialize this to representables, which are these specific kind of tight discrete vibrations. Then if you have a tight object B, so that you can build this thing in the plumbus, then the associated representable coprocheaf, or generalized coprocheaf, so the mapping to omega associated to it, is always a laxity morphism, and that we knew, sort of, we could expect, but also we know it is strong precisely when B is T Cartesian at little b. Okay, so this is closing the question of what kind of representable coprocheafs are in fact strong when there is some algebraic structure around, which is this, when B is T Cartesian at B. And now, if you remember my talk from February, which are excused not to remember because you're not me, but the conditions that I spelled out in the specific case of representable behavior were in fact all of this nature. So if you had a system, then this system better be like the represented behavior functor. Then the behavior functor was for the behavior functor to be compositional, you needed the system to be a commutative comonoid in the system theory. So the system theory was Cartesian at that for its monoidal part. And then it needed to be what I call observable. And observability was the definition of T Cartesianity for the being an algebra of a double operad part of the structure. Okay. And then you had a condition on the double category below, which again is, which was the Spanish condition, which we've seen above, was exactliness of T Cartesianity. So this is the applications part. And I think this is it for me. Yay. Now, there is a second part of this talk, which is, if there is time, which I don't know, we can actually go through the construction of some two classifiers.
We might have to cut off the recording there, but I'm certainly interested to hear more about this later. Okay, let's take a take. Maybe we have time for a few questions. So I was a bit confused about.
That's understandable.
Sorry. Saying about like you've got these commas if you've got a lax morphism and a colax morphism, and so you need to require that to be strict for the colax to be like an example of a lax morphism. But then you say you can't really do the comma if it's merely strong. I was confused as to why you required tau to be strict rather than strong. Or that.
So where is it? Here.
Yeah.
So I think that's actually a good question, because so the way you construct the algebra structure on the comma, I think you just need the other morphism to be like strong, not strict. But lax is strict. and I trust Lac more than myself.
Oh,
So I don't know if any of you has a better guess about this.
Yeah, I think that the reason we use strict is because we're doing the lax over strict uh um enhanced category. But
was it lax over?
Yeah, why not Lac over pseudo, right?
that's a good question. I don't
But the like, yeah, just the point you said there's some sort of comma construction that makes sense if
pullback
it's
preserving thing used the strictness, I believe.
All right.
Our pullback preserving one used the strictness. The thing is that often, even if it's like an isofibration, it doesn't matter as much. It has to do with
Yeah. Like,
yeah.
so that's the part. Well, we assume it's a vibration, and the vibration part. So, okay, he's talking about this result we proved, right? Where you can pull back vibrations along Lax morphisms, strict vibrations, like as in strict with respect to the algebra structure.
Right.
And the vibration there, like the reason this pullback exists is that the vibration allows you to sort of like lift the collaxator of the thing. Yeah, it's collax. Okay, no, sorry, I do a lie. So it allows you to lift the laxator. Okay. But then like when you construct the comma, so this is not about that, right? When you construct the comma, what you do is basically, then there you have a morphism, and then you like do some operations on a bunch of morphisms. And now what you need to do is, well, you do a bunch of operations on one, a bunch of operations on the other, and now you need to like reconstruct the morphism in a sense. And the way you do that is by precomposing with the collaxator, and postcomposing with the laxator.
Right.
So you're taking like collax
Oh,
over lax.
Right.
Okay. And then this allows you to precompose with the collaxator of the first and postcompose with the laxator of the second. That allows you to like define the morphism unit within the comma.
Right.
I think I know why.
Mm.
When you have the comma square, whatever, like this, and then the universal one, here, this such an outer one here, sorry, so such an outer one factors through the comma.
Comma has to factor strictly.
Yeah,
Mm.
that's it.
It makes
Through
sense.
Z.
Yeah.
If you want these to be equalities, then you need the one of the sides to be strict.
Right. Okay.
And that just comes down to that you're asking that you're literally over the same one. Where I think in the pseudo one you end up being able to move over by a pseudo, where maybe I'm wrong.
Okay. But do those two somehow correspond to the collaxator and laxator for the algebra morphisms? Is that?
Maybe I'm not sure. It's a good question.
Mhm. But yeah, if it's not about constructing the algebra structure of the comma, like there's no requirement. No, then it should be about that.
Yeah.
And if it's not about that either, then it's just not a requirement.
But I think, as you mentioned, somehow the story really wants to be that you have laxes and collaxes, and you can classify things like.
Which makes it seem like strong should be good enough in
Yes. However, I guess I mean, like in practice, it's actually strong. None of these things actually are equal to the coherence problems. Go all the way down. Yeah.
I did have one other like sort of vague question. Like, do these conditions as up vibrationally Cartesian, or those conditions somehow like it looks familiar from familial two monads, right? Sort of, and that they
I'm not familiar. Like I know the paper and the thing.
okay, yeah.
I don't know.
Okay, yeah.
Okay.
I'm just wondering if that's some sort of.
So you're saying that You think this is a kind of familial to monad?
Well, yeah, I don't know if Cartesian, I think maybe Cartesian is,
It is true that every familial to monad is opfibration Cartesian.
okay,
And that's in Weber's, or like if you go far down in that big familial two functors Weber paper, it proves that they're Cartesian and that they preserve split vibrations,
Really?
which includes discrete vibrations.
Oh, that's cool.
Hmm.
That's a good.
Yeah, so the familial two monads are an example of this, I believe. I don't know about actually the part 3. Actually, I should say that it's part 1 and 2. Sorry, part 1 and 2.
Right,
But-
is that, it's Cartesian, it's not like part of the
Oh,
definition.
sorry. No, it's Cartesian at all morphisms. So yeah,
Yeah.
sorry, it is an example.
Okay, and then Cartesian are all type discrete. Right, okay.
So in principle, that should include all these two algebraic structures that we're hoping to apply this to, but that requires understanding Weber.
Right, and I guess there's like there's this F category structure that's not in Weber's.
Oh,
notion.
yeah, that's true. But you can do this on a chordate one, and then the trick is we wanted to iterate it. So like as soon as you do it once, you go into algebras of line
Right,
chemistry.
okay.
So like
Yeah.
so you even though we started by not thinking about enhanced two categories, but because you only ever classify the strict ones, it
Right,
suddenly
okay.
presents itself that you have these two notions of morphism and
Yeah.
you know,
Yeah, maybe I didn't say that, but like why we want to iterate it? Because of course, like our goal is to apply this to the structure algebras of double algebras of double operands.
Hmm.
And the idea is to construct this structure in steps. Right? And there are steps which is add stuff, and those are taken care of by Maziti's result. Like luckily, because in principle they might not, but in practice they are. And there are structure steps in which we needed a new result. So the idea was, okay, we had the monad structure, we had the double category structure, we had the algebra stuff, and blah, blah, blah.
Mhm.
So you lift your two classifier until you're done. That's the general idea.
Right, okay, and you're inevitably getting F categories even if you start with chordate things.
Yeah. The F part is always that you're gonna be strict in your algebraic structure. That's the only.
the algebras themselves are also strict morphisms. So when you iterate it, they're strict algebras for the first thing.
Right.
The algebra structure for the second monad you iterate on is a strict algebra for the first one.
Right.
Yeah.
I don't know if there's any theorems about distributive laws and lifting monad two monads to last algebras or something. Some weird kind of stuff.
Okay, are there any further questions? If not, let's thank Matteo again.
Just a